Hello, in this video we are going to solve Schrodinger wave equation for a special potential function, that is delta function potential. Before going to solve the wave equation, we would like to discuss why it is important to solve the Schrodinger wave equation for the special potential function. Okay, first of all I would like to define delta function. Delta function is written as del of x, and the value of del of x is infinity when x is equal to 0 and 0 otherwise. And please remember this is not the complete definition. The complete definition is, yes, when we integrate this delta function from minus infinity to plus infinity, we will get plus 1. Okay, now I would like to discuss why it is important to solve this Schrodinger equation for this special kind of function. Some mathematician will say it is not a function at all because it is not defined as x equals 0, but in physics it is very helpful. It comes in many cases in many branches of physics. So okay, now let's come to this graph. This x-axis is labeled as r. R is nothing but the radial distance from the origin. It is in the polar coordinate, and in y-axis it is nothing but E is the energy. So let us consider some potential function. It is some arbitrary potential function drawn by the green color, and in this graph also these green colored graphs are some potential function. And now let us consider some system with total energy E dash. So we would like to draw the graph for E dash. So it will be something like this. Let us consider. So in classical mechanics, what will be the behavior of a particle for this total energy E dash? So what is the total energy of a system? Total energy is nothing but the summation of kinetic energy and the potential energy. Okay, in this graph this is the total energy, so and this is the potential energy, so this difference will appear as the kinetic energy. Okay, now let us some particle is approaching from infinity to the origins. This is the radial distance in the x-axis, so this is the origin where radius distance is 0 at this point. So some particle is coming from the origin towards, sorry, particle is coming from the infinity towards the origin. So at this point the kinetic energy will be this much, at this point kinetic energy will be this much, but when it approaches this point the kinetic energy will be decreasing monotonically. So at this point kinetic energy will be 0, and beyond this point towards the origin kinetic energy will be imaginary. In classical mechanics it is not possible to have kinetic energy to be imaginary, so we won't find any particle at this region. So what will happen at this point is that the particle will bounce back and will again go back to the infinity. And if, let me draw it by another color, and if the total energy is this much, so we won't found the particle outside this region, so it will bounce back to and fro in this region. It is nothing but the simple harmonic motion. And now let us consider this artificial case at, let us say it is r equals r dash and r double dash. At these 2 points the potential energy is standing to infinity. At this whole region it is standing to infinity, and in this region also. So if a particle is at this point, so I mean the total energy is this much, it will just bounce back to and fro in this region, so it will be confined in this particular region. Now let us go back to the quantum mechanical example. So in quantum mechanics there is a special phenomenon that is scattering, sorry, quantum mechanical tunneling. So even if the total energy is less than the potential energy at some point, like we had found in the step potential where total energy is this much, in classically it is impossible to find a particle. So this is the total energy, it is the step potential is like a is phi of x, and this is the total energy. So at this point, in this region, the total energy is less than the potential energy, so classically it is impossible to find a particle at this point. But in quantum mechanical, if we solve the Schrodinger wave equation, we will see that it is possible to find a particle in this region too. So in this case also, like we if we, even if it is impossible to find a particle in this region, if potential goes down like this, we will definitely find the probability of finding this particle is not exactly equal 0 at this point. It will tunnel through this potential barrier. Okay, but in this case, like as the potential goes to infinity, so we won't find any point particle in this region because it is going to infinity. And if you solve the Schrodinger equation for this special function, we will find that the particle is confined in this special region only. So out of these two examples, this condition, this state is called bound state, when the particle is confined in between some two particular points or in a particular region in space, and this condition is called scattering state. Where the particle comes from infinity, slows down, bounce back, or it speeds up again. So these are the characteristics of scattering state, and the characteristics of bound state is that it will be the particle will be find, or the probability of finding the particle will be finite at some particular region only, or outside that region probability of finding the particle will be exactly equals 0. So as in quantum mechanics, even if the potential height is finite, it will penetrate through the potential height. So what matters in the means what decides whether a system will be a scattering state or in a bound state is that the potential at in the infinity. So I will write down the condition for the scattering state and a bound state. So for finding the a special system to be in a bound state, the condition is that the total energy will be less than the potential energy in the negative infinity and in the positive infinity. And if the total energy is greater than the potential at the negative infinity and the potential at the positive infinity, it will be in the scattering state. Now let us discuss why it is so. It is very easy to understand. For let us consider some arbitrary potential function. If the total energy is less than the potential energy, let us consider a classical mechanical state only first. So if the total energy, this is energy and this is the total energy, it is less than the potential energy, so it is in a bound state. And for a energy greater than the potential energy, it will be in the scattering state. But in quantum mechanical state, even if the total energy is less than the potential height, there is a finite probability of finding the particle in this region also and in this region also, due to the quantum mechanical phenomenon that is known as quantum tunneling, as I have already mentioned. So it doesn't matter at all if the total energy is less than the potential energy at some finite distance, or it is greater than or less than the potential at some finite distance. So what matters is that the potential in the negative infinity and in the positive infinity. If it is less than the potential, then it is bound state, or otherwise it is in the scattering state. and generally potential goes to 0 in the positive infinity or in the negative infinity in the very general case. So the condition reduces to, for bound set it reduces to energy less than 0, and for scattering set it reduces to energy greater than equal 0. Now we will look at some mathematical formulation of Dirac delta function. As I have already written, the definition of Dirac delta function is this one, and when we integrate the delta function from negative infinity to positive infinity, the total area is equal to unity. So if you draw the graph of delta function, it will be something like this. As it is infinity in the origin, it is very narrowly spiked in the origin. So now I would like to show you some other definition of delta function. If I draw a rectangle of length of height, in this case height 1 by epsilon naught, and this width is epsilon naught, then the area will be epsilon into 1 by epsilon, that is equals to 1. When epsilon goes to 0, it will be something like this. When we keep on decreasing, it will be something like this and this, and if again we keep on decreasing, the height will be increasing and this weight will be decreasing. So when it tends, epsilon tends to 0, at very near points of 0 it will be behaving like delta function. And another definition of delta function is this one. This is normal distribution function, and sigma is nothing but the standard deviation, and when sigma tends to 0 it will approaches the delta function, and we can write sigma as like this is full width at half maxima, and this is equals to 3.25 sigma. I'm sorry, this will be equal to 2.35 sigma. Let us look at some look at some special properties of delta function. Like if we multiply the delta function with some other function and integrate it from negative infinity to positive infinity, what will we get? So the function, this multiplication will be 0 everywhere except at x equals 0. So we can write it as, because the delta function is 0 everywhere except at x equals 0, so we'll get f of 0 delta of x d of x. As it is constant, we can write it outside the integration, and delta of x, and this is term is equals to 1 from the definition, so we will get x equals 0. And if from definition, if delta function can be written in this form also, and the definition will be infinity when x equals a, not 0 in this case, and 0 otherwise. So this property will be used in some derivation later case, so I would like you to remember this. Now I would like to show you some other example where the delta function comes into play. And as you know, the Gauss divergence theorem is that divergence of some vector a, if you integrate it in the whole volume V, and it will be equals to the integration of the factor a over the surface enclosing that volume. If we take a to be divided by r square, and this comes in electrostatics. So this the definition of delta function we are going to derive here is especially useful in electrostatics. Still I'm going to derive it for you as in a in one go. So if we calculate the divergence of A, we will get 0 here. If we can calculate it, the divergence will be in spherical coordinate here. And if we calculate the right hand side in r cap, see, dot dr will be here in this case r cap r square sine square theta d theta d phi. If we calculate it, we will get this is equals 4 pi. So in this equation, in the left hand side we are getting equals 0, in the right hand side we are getting 4 pi. So this is a contradiction. So how do we solve this contradiction? By introducing delta function. As in this case we can see that the integration of that factor a is independent, though we are integrating this in the whole surface. The result of integration is 4 pi, that is independent of the surface. So if we keep on decreasing the surface area if to 0, we will still getting 4 pi. If area tends I mean this should be area factor tends to 0, then also we will getting this integration equals 4 pi. So in the same case as the potential is infinity in the origin and the integration is 1, if we integrate it from the negative infinity to the positive infinity, this we are getting the same characteristics in this case also. So we define the divergence of a in the right hand side we were getting 0, but in case we should get 4 pi, and there should be some other term so that it makes 4 pi when we integrate it through the whole surface. So we define divergence of a is nothing but let me write this 4 r square equals 4 pi del cube r. So this is a three-dimensional delta function. That means if we go to that point from all three direction, it may vary depending on the choice of the coordinate system, but let me this is in the spherical coordinate system. If in case of like in Cartesian coordinate system, if we go to the origin from x-axis, y-axis or z-axis, it will be a three-dimensional delta function. So it is infinity in the origin only and is 0 otherwise. So there is another term being multiplied with this delta function, that is 4 pi. So in this case when we integrate this a here, so it will be 0 everywhere, and only in the origin only it will be giving some result, that is 4 pi. So if we integrate this one, this is 4 pi del cube r, and this is the for a whole volume. If we are integrating in the left hand side, we will be getting 4 pi, and the integration of this will be, as in case of, we can break it in three part, one for each dimension. So for each dimension it will be integration from in negative infinity to positive infinity, or from two extreme limits of that special dimension. We will be getting the integration will equals to 1. So this whole integration, if we integrate for the whole volume, we will getting it equals 1. So 4 pi into 1 equals 4 pi. So there isn't actually any contradiction arising when we introduce delta function here. So this is the use of delta function actually. Now let us come to the main problem. Now let us write the Schrodinger equation, time independent Schrodinger equation. In this case, the potential is delta function, and let us consider a special delta function, something like this. It is in the negative direction, like like let us consider some alpha is being multiplied with the delta function, and there is a negative sign for like this. This is a delta function well only. Okay, now let us write the Schrodinger equation again, inserting the special potential function minus del. Okay, in this video we will consider only the bound state, that is energy less than equals 0. I will make another video for the scattering state, that is energy greater than equals 0, and the link will be in the description below. And now let us solve the Schrodinger equation for the special energy. And now for the case 1, when x is less than 0, this Schrodinger equation will be reduces to delta of x equals energy of psi of x. So the solution can write it in another way, psi of x minus of 2me by h bar square. Here we can introduce another variable, that is k equals minus 2me h bar. By definition energy is less than 0, so k is real and k greater than equal 0. So this Schrodinger equation will be reduces to k square psi of x. The solution will be nothing but psi of x e minus kx by kx. You can verify whether it is a solution or not by substituting psi of x and double differentiation with respect to x of psi of x in this equation. So that's in equation 1. And now for case 2, where x is greater than 0, again the potential and energy is 0 in this case, so the equation will be reduces to the same equation here. So there will be minus 2me by h bar. We can like same case substituted here. So equation the solution will be same, but the unknown constant will be different here. Yeah, minus x by d of and let us check whether these two solutions are physically acceptable or not. When in this equation, this is for x less than 0, so when x tends to negative infinity, this term will blows up. So like by definition psi of x should be finite in the whole domain. So for x less than 0, this term a should be 0, so that psi of x is finite everywhere, p of k of x. And again for x greater than 0, and this term will blows up when x tends to infinity, as it is the case for x greater than 0. So the solution will be psi of x c of e to the power minus k of x. Now for solving the unknown constant, we'll have to apply the boundary condition. The first boundary condition says that psi of x should be continuous everywhere. So for and this function is continuous everywhere, and this function is also continuous as exponential function is continuous, and the point of discontinuity could be x equals 0. So let us check the value of function at x equals 0. So this will be b only, and in this case it will be c. So as psi of x should be continuous, so at x equals 0 this should be b equals c, as this is equals b at x equals 0, and this is equals c at x equals 0. For the function to be continuous, it should be b equals c. And again, the second boundary condition says that first derivative of psi of x should be continuous everywhere when there is a actually when the potential is finite. But in this case the potential is infinite at x equals 0. So what will we do for see why it is this function, like first derivative of psi of x is continuous everywhere? To see that, we will have to look at the Schrodinger equation again. That is, if you integrate the Schrodinger equation from negative infinity to positive infinity, what will we get? We'll get from negative infinity to positive infinity d of x, negative to positive d of x. Okay, the first term will be first derivative of psi of x, so it will be minus okay, let's write it psi of x plus derivative first derivative minus infinity, and this again I should write as it is d of x again minus infinity. It should comes outside of the integration sign, psi of x. In general case, the side, that is the eigenfunction, goes to 0 in the negative infinity and positive infinity. That is why it is 0. Again, this term also goes to 0 as the psi goes to 0 in the positive infinity and in the negative infinity. So this psi of x, the first derivative of psi of x is continuous everywhere, but in this case we are dealing with a special potential function, that is a delta function. This we can write it as the change in the first derivative of, as like there is nothing to consider the infinity here. We can like just consider some like sorry, d of psi of x, d of x, let us consider some small number epsilon naught. So as in this case the continuity as at x equals 0, that the delta function is defined, delta function goes to infinity, no, in this case negative infinity at x equals 0 only. So we will have to make this epsilon as small as possible. So this will go to 0, and let us write the delta function. Delta function is defined as minus alpha of del of x psi of x dx in this case, and minus epsilon naught to pass epsilon naught, and we can write it as the change, minus sign cancels out, we can write it as the change of first derivative of psi As from the definition of delta function, this will come out of the integration, and like when we integrate it from plus infinity to minus infinity, or any domain where the where this goes to infinity, like if we integrate it as x goes to infinity at x equals 0, if we integrate it from some -1 to +1, we will get the integration of del of x equals 1. If we integrate it from +1 to, even if it is 1.1, we will get it equals 0, as the delta function is equals to 0, and as the epsilon is a positive number, and like epsilon naught could be zero point 0.1, if we integrate it from minus 0.1 to plus zero point 0.1, the delta function will be infinity at in between these two boundary points. So if we integrate it from these 2 points, we will get it equals 0, and this psi of x will come out of the integration sign. It will be psi of 0, as we have discussed already. And what will be left here is psi of x, d of x. This is from the definition of delta function. um, if we need it, I can derive it again, but this is just the time consuming, as I have already derived it. Psi of x will be equals to 1. So the change in the first derivative of psi of x will be equal to minus 2 psi of x alpha twice m by h bar square. Psi of 0 is a here, or not a. As we have seen, it is at equal 0, it is b or c. We will write only b only, as c equals b only. So it is b alpha twice m by h bar square. So what was psi of x for x greater than x less than 0? It was b into sorry, k of x, and for x less than 0, for x greater than 0, it was c. Nice. And the right hand side derivative of this function, sorry, left hand side derivative of this function will be b of e k x. This is left hand side derivative, and the right hand side derivative will be minus c k e to the power minus k of x. So changing the first derivative of psi of x at x equals 0, this will be 1, this will be 1. So and c equals b, so we will write it at b only. So there, sorry, there will be a k term, so it will be minus of 2b k, and it equals, from this equation, it equals to minus b alpha twice m e bar square. So b cancels out, 2 cancels out. What remains here is that k equals m of alpha by h bar square. And what was k from the definition of k? It was minus 2m e by h bar, where E was the total energy of the system, m of a h bar square. When we solve it for the energy, what will we get is that energy equals minus h bar square, sorry, not h bar square, it will be m alpha square to 8 bar square. And one more thing is remain is that we have to normalize psi of x from minus infinity to plus infinity psi of x dx, and it is, and it should, sorry, the square it is, it the psi of x, the angular function should be square integrable from the definition, and it should be equals to 1, and it is from minus infinity to 0, it is a equals e to the power k of x dx, it's the square term is there, and 0 to infinity a of e to the power minus k of x square term is there equals 1. What will we get from here is that not a, it was b here. B square is equals to k, so b will be equal to root over k. So, and from the definition of k, k was equals to, as we had got here, is a k was equal to m alpha by h bar square, so root over k will be m alpha root over h bar. So the solution, the eigenfunction will be psi of x, and first will be, there will be the constant term b is equals to here m alpha h bar. Then for a for a x less than 0, it was plus term is was there k x, we can write down the value of k here, it should be equal to m alpha h bar. K was here m alpha bar square x, and x less than 0 here, and for x greater than 0, h bar e to the power minus kx m alpha h bar e to the power minus of m alpha h bar square x. And if we combine these two equations, we can write psi of x as m alpha h bar e to the power m alpha h bar square minus, we can write the modulus of x from minus infinity to plus infinity. There is no need of writing here, but still I'm writing here. So this is the solution for the time dependent Schrodinger equation for the special potential function, that was in this case minus alpha into del x. This is the delta function, and we will discuss the other problem, that is for energy greater than equals 0, that is the scattering state, in some other video, and link will be in the description below. Thanks. Done. We can summarize the result and the problem in this. So this is the special potential function, and this is the solution. Thank you for watching.